Hi, and welcome to this section of the Advanced Calculus 2 tutor. And in this section we're going to tackle the sometimes daunting looking section called Trigonometric Integrals, okay? So there's this section in Advanced Calculus 2 called Trigonometric Integrals. They're usually the pages just bleed with a bunch of examples that have a lot of trigonometry in there and simplification and other things. And those are challenging because there's no one way to do them. You just sort of have to get a feeling for what you need to do, and the only way you can do that is to see some examples, okay? So what we're going to do is we're going to tackle these types of problems in this section. Now don't confuse this section with something you've already studied before on my previous DVD, which is called trigonometric substitution. That's when you are making a substitution of a very specific type that deal with the trig angles into the equation. This is trigonomic integrals, and let me give you an example of what trigonometric integrals. Let me give you an example of what that might look like. The first form of the trigonometric integrals that you'll see are of the form of the integral of sine to the nth power of x times cosine to the nth power of x dx. Okay, so here is the general case. You have a sine function raised to a power, and you have the cosine function raised to a power, and these can be different numbers. So you might have sine cubed, and you have cosine squared, or something. And basically, these all become an exercise in trying to factor out and use different identities, and and make it simpler. And that's basically what it all boils down to. Okay, so the basic way I want you to tackle these kinds of problems are as follows. There's really no one way to do these things. I mean, you have to play with them, but I'm going to try to give you some guidelines. So what you say is, for instance, in general, if m or n, which are these exponents here, are odd, okay, if they're odd, okay, then here's what you're in general going to do. This is just an in general kind of thing. You're going to factor out the one with the odd exponent. Okay, we're going to get problems to show you what I mean by that. So if this guy's odd, if this is sine cubed, he's odd, so you'll factor out one of the signs, leaving sine squared. So you'll factor him out, you'll factor the one that's odd out. You'll rewrite the function using the famous identity that you guys all know, cosine squared plus sine squared is equal to 1. Okay, you'll rewrite using that, and then you'll use substitution. Substitution, if I can spell right. Okay, so that's the basic cookie cutter thing. Now you can't get too wrapped up in this formula here. I mean, it's not going to be perfect, but it's going to get you through most of the cases. Okay, so let's go ahead and do one problem here, and I'm going to go ahead and start the problem right below here, and I'm going to try to fit it in here. Let's say you're going to have the integral of sine cubed x, so sine of x all raised to the 3 power times cosine squared x dx, and you want to evaluate that integral. What you want to do is you want to beat this thing into a shape so that you can do some sort of substitution on it and get it to cancel. So using our cookie cutter thing, which is sort of a first place to start, this is m and this is n, okay? This is odd. So I'm going to rewrite this integral as sine of x times sine squared of x, that's what I mean by factor him out, that's all you're doing, times cosine squared x dx. That's all we've done. We've just pulled out one of these signs, okay? And the next thing I'm going to do is I'm going to rewrite this sign using this identity right here. So I'm going to say this is going to be equal to the integral of sine x, okay, times 1 minus cosine squared of x. This guy is equal to sine squared. Think about it. Sine squared is 1 minus cosine. So all I've done is plug that in here, times cosine squared of x dx. Okay? Now here's where the fun starts. Think about what I've done and why I've done it. Okay? If I take u to be equal to cosine of x, Okay? If I take u and do a substitution to be equal to cosine of x, I'm going to have a u squared here and a u squared here. And when I take the derivative of cosine, I'm going to get negative sine. It's going to end up being on the bottom, and it's going to cancel with this sign. So you see, that's why I factored them out. I factored them out so that I could choose a clever substitution, this cosine, so that when I take the derivative, it's going to end up canceling. You see, I couldn't choose a nice substitution here. If I put u is cosine here, I can take the derivative, I'll get sine, but that's not going to cancel with this. I've still got 3 more sines here. But by taking one of those sine squareds and writing them as cosine, I can get the entire integral in a good form. So what I'm going to do next is I'm going to switch colors, and right over here on the side I'm going to say, let's say u is equal to cosine of x, then du dx, derivative, is just going to be equal to, derivative of cosine is negative sine of x. Okay, and then now let's go ahead and solve for dx, because that's what we always have to do. It's going to be equal to negative 1 over sine x du. Take the dx over here, move 1 over sine over here. Dx is 1 over sine of x du. Okay, now what I'm going to do next is I'm going to switch colors entirely, just because I want to break up the board, and I'm going to show you how the substitution changes the game. Okay, integral of sine x times 1 minus u squared, because now I'm just plugging in what I've defined to be u, times u squared here, times dx, which I've defined here, which is negative 1 over sine of x. Now look, this is what we've done here, and by the way, this is now du. So we need to get an integral all in terms of du, but fortunately sine of x cancels, and now that's what we have. We now have the integral of let's say we'll put a negative sign out here, we'll pull the negative out. We have the integral of 1 minus u squared times u squared, okay, du, okay? And we'll just multiply the u's in, and so we'll have negative integral u squared times 1 is u squared minus u squared times u squared is u to the 4th, okay, du. And just for grins, we'll take this negative and we'll chunk it right back in there, and we'll say we have the integral of u to the 4th power minus u squared du. We just negate the signs, and so that's what we have here. U to the 4th power minus u squared, okay? So what we'll do now is we'll just take the integral. We can do that. This is a polynomial. The integral of u to the 4th power is 1/5. 1 plus the exponent is 4 plus 1 is 5. 1/5 u to the 5th power minus, this one is going to be 1 over exponent plus 1 is 3, 2 plus 1 is 3, u to the 3rd power plus a constant. Okay, so I have the answer, 1/5 u to the 5th power minus 1/3 u to the 3rd power plus a constant. And now I just plug in my definition of u, which is going to be 1/5 times cosine to the 5th power of x minus 1/3 times cosine to the 3rd power of x plus a constant, and that is the answer. 1/5 times cosine x to the 5th power minus 1/3 cosine x to the 3rd power plus a constant. So you see, this trigonometric integral stuff, it's challenging to know what to do, but that's what working the problems does for you. When you have sine times cosine and you have powers, if one of them is odd, factor him out, write the other guy in terms of, if it's a cosine, sine, write it in terms of cosine and vice versa. And what that's going to do for you is allow you to pick a substitution that will cancel with what you factored out. Okay, now the next problem goes something like this. Integral of sine to the 8th power of 6x times cosine to the 3rd power of 6x dx. And I want to solve that integral. I want to do that integral. Well, you see, right now I see I have a sine to the 8th power and a cosine to the 3rd, so I have an odd power of cosine here, and I know I can use that and I can do my factoring technique, but right away I do not like this 6x that's running around here. I just like to have my integrals clean and simple with just an x in there, so I'm going to get rid of that thing first. The way I'm going to do that is I'm going to do a simple substitution for 6x. U is equal to 6x. So if I do that, then du dx is just going to be equal to 6. Derivative of 6x is 6. And then solving for dx, because that's what I'm going to need later, it's going to be 1/6 du. Okay? Solving for dx is 1/6 du. So let's go ahead and just do that right now and say, well, it's going to be sine to the 8th power of u times cosine to the 3rd power of u times 1/6 du, because plugging in for dx is 1/6 du. Okay, is 1/6 du. So what I'm going to do now is I'm going to pull out the 1/6 and say the integral I have left over, I'm going to do what I did in the last section. I have an odd power in cosine here, so I'm going to factor one of those guys out. So I'm going to have the 8th power of sine times u. I'm going to have cosine squared of u, and I'm going to factor one out, so I'm going to have another cosine of u du. All I did was I split this cosine cubed up into two little terms, cosine squared and cosine. And the reason I did that is, just like in the last problem, I'm going to use my little identity. I'm going to rewrite cosine squared as 1 minus sine squared of u times cosine of u du. I'm going to rewrite this here. This is the only thing I did, is rewrite this cosine. And that comes from the identity you should know. Cosine squared plus sine squared is equal to 1. That's sort of a universal thing. Okay? So why did I do this? Because you see, if I choose a substitution in sine, when I take the derivative I will get cosine, it will cancel with that, and then I will be left with an integral all in one variable. So I've used the variable u here. I can't really do that again. So here I'm going to use the variable s for my substitution. S is going to equal to sine of u. So then ds du, derivative of sine is cosine of u. And so then du, which is what I'm going to need to plug back into here, is going to 1 over cosine of u ds. Okay? And I'm going to go ahead and switch colors here just to kind of denote that. We're turning the corner here. 1/6 times the integral of sine to the 8th power, which is s to the 8th power, times 1 minus s squared, times cosine of u times du, which is defined as 1 over cosine u du. Now you can see right away that the cosine cancels with the cosine, and that's why we did it. Now we have, whoops, I made one mistake. This is not going to be du, it's going to be ds. Okay, because that's what this is equal to here. So now you see I have an integral in s only, ds. Okay, now I'm going to distribute this s in and continue on with my simplification and my integration. 1/6 times the integral of s to the 8th power, s to the 8 times 1 gives me s to the 8th power, minus, multiplying these two together, I'm going to have s to the 10th power ds. Because s to the 8th times s squared, you just add the exponents together. Now I can actually do this integration. This is a simple polynomial integration. So what you'll have here, integration of s to the 8th power is 1/9 s to the 9th. And integration of this is 1 over 11 s to the 11th. That's your simple polynomial rule of integration, 1 over exponent plus 1, s to the exponent plus 1. And of course you have plus c because it's an indefinite integral. So now we just clean up the simplification here. 9 times 6 is 54. Okay, s to the 9th minus 6 times 11 is 66 s to the 11th plus a constant. Now we just substitute back in what we know s is, which is 1 over 54. S is sine to the 9th power of u minus 1 over 66 sine to the 11th power of u plus a constant. Now we still have our function in terms of u. We go all the way back up to the beginning and we found that u was equal to 6x. So it's 1 over 54 sine to the 9th power of 6x minus 1 over 66 sine to the 11th power of 6x plus a constant. And that is the answer. 1 over 54 sine to the 9th power of 6x minus 1 over 66 sine to the 11th power 6x plus c. So it's the same kind of thing. You just go methodically. I wanted to get rid of the middle things here, so I chose a simple substitution to get rid of that. The 1/6 comes out as a multiplicative all the way down because of it. And then when we're presented with this, you just factor out one of these odd numbers here, because one of these guys is odd, so that's what we do in these cases. We factor out one of them, and then we rewrite the cosine squared as a sine squared, and then we choose a clever substitution to cancel with the cosine, and then the rest of it is just a polynomial integral. Okay, the rest of it is just a polynomial integral. Okay, now in the last type of problem that we had sine to a power times cosine to a power, and we said that when one of those guys was odd, we want to factor one of those guys out, use the famous identity sine squared plus cosine squared is 1 to rewrite part of the integral, and then choose a clever integration path to make a cancellation and then go from there. So what do you do when you don't have an odd one of those guys? What if you have sine times cosine and you have powers but neither one of them are odd? Well, that's what we're going to study now. So here is sort of some guidance here. You can't really make these cookie cutter. I'm trying to give you some hints, okay? If m and n, which remember these are the exponents in the sine cosine integral, are both even, okay, then you use the trig identity to simplify. And these are some identities that you'll probably need to use. Sine x times cosine of x is equal to 1/2 times the sine of 2x. That's one that you'll probably use. You'll also probably use sine squared of x is equal to 1 minus cosine 2x over 2. You'll also probably use cosine squared of x is equal to 1 plus cosine 2x over 2. Okay, so what you're going to do is, and we'll do a problem here and show you what I'm talking about, but if you have even, you're just going to basically have to use some identities to try to beat it into shape, and then frequently you'll have some useful integrals to help you out. If you can memorize these, if you can commit these to memory even just for your test, you'll really help yourself out, okay? Because they're very useful and they turn up a lot. Integral of sine squared x dx, just the integral of sine squared, is 1/2 x minus 1/4 sine of 2x plus a constant. And of course, cosine, the analog of x dx, is equal to 1/2 x plus 1/4 sine of 2x plus a constant. I'm not deriving these. I'm not doing anything other than writing them on the board to show you that they're true. They're useful though. It doesn't mean you have to have them. I mean, it doesn't at all. It just means that they're very useful if you can program these in your calculator, if you can remember them or whatever. These identities are helpful. These integrals are helpful. So let's go on and do a problem and you'll see what I'm talking about. What if you have the integral of sine squared x times cosine squared x dx, and you need to solve that? Well, you can't really do the whole factoring method thing that we did before because neither one of these is odd, okay? I can rewrite this cosine as 1 minus sine squared. I can do that, but that doesn't really help me all that much because I'm going to have a lot of sine squareds and cosine squareds running around. Okay, here's one way that you can proceed, and these are, you know, remember back in trigonometry when you were given an identity and you were told prove the identity. Well, you had to know your identities well, and you had to play with them until you got the result you wanted. I mean, that was just part of the game. You had to do that. These integrals are kind of like that. You basically have to know some identities, memorize them, write them down something, and apply them and use them, and then finally you'll get to a nice cute substitution that'll work. And I know it's not very cookie cutter and it's not very comforting to tell you that you just have to play with it, but it's true. You just have to play with it and get some practice. So in this case, I'm going to show you a little something here. What if I were to rewrite this guy as sine of x times cosine of x squared dx? I mean, I've changed nothing. I've just taken this and I've written it all together and squared it. So you square each term individually, you get back what you started with. So I've changed nothing, okay? Now you can use the identity, okay, that we just looked at over here. This one right here, sine times cosine is equal to 1/2 sine of 2x. You see why I told you these identities would be useful there for this reason. So if I do that, I say integral of 1/2 times the sine of 2x, okay, squared dx, okay, dx, okay. And then what I can do then, just to make it even clearer, is I can take this 1/2 and I can pull him out because he's going to be squared. He's going to be a 1/4. So this is going to be 1/4 times the integral of sine squared of 2x dx. Okay, so all I did was I made it sine squared of 2x dx. Now let's go ahead and do a quick substitution for this part in the middle here. U is equal to 2x du dx is equal to 2. Just taking the derivative of that is just 2. Okay, there's your simple polynomial derivative there. And then solving for dx, because that's what I'm going to need for my substitution, is 1/2 du. Now let's go ahead and plug his little guy there in there. So it's 1/4 times the integral of sine squared of u dx, but I need to substitute, so I'm going to have 1/2 du. Okay, I'm going to have 1/2 du after that substitution. Now let's pull out the 1/2. I'm going to have 1/8, 2 times 4 is 8, times the integral of sine squared u du. Now you see why we finally did that. You resolve this integral down to a sine squared of u, and I told you that it's very useful integral. Sine squared x dx is this guy right here. So I'm going to use that fact, and I'm going to say it's 1/8 times 1/2 x minus 1/4 times the sine. Actually, it's going to be 1/2 u, because I'm still talking in terms of u, minus 1/4 sine of 2u plus a constant. All I did was I took this integral, that's a useful integral. Most of the books in this section of the textbook give you a couple of useful integrals that are helpful. I put 1/2 u minus 1/4 sine 2u plus a constant, and now let's just simply substitute in for what I know, and let's go ahead and multiply in while we can. So 1/8 times 1/2 is 1/16 u, which is 2x, okay, minus 8 times 4 is 32, 1/32 sine of 2 times u is 2x, plus a constant. Okay, now let's simplify everything here. 2/16 is going to be 1/8 x minus 2 times 2 is 4, so I'm going to have 4 on top here. So right here what I'm going to have is 1/32 times the sine of 4x plus a constant. So this is the final answer, 1/8 x minus 1/32 sine of 4x plus a constant. So I tried to give you some basic technique to use. When you have even numbers here, you want to use these identities that I gave you here to simplify them, and you're generally going to try to beat the integral into a form like this or like this, and you can usually use these techniques to be able to do that. It's not very cookie cutter, but it's kind of like those identities that I talked about earlier in your basic trig. I mean, you have to be willing to play with it, try different identities, see if you can get a simplification, see if you can get something to cancel, choose a clever substitution of u to get it into an integral that you know how to solve. Okay, in the last problem type we had sine to a power times cosine to a power, and we had a couple of different flavors of problems like that. Now we're going to tackle problems that have tangents to a power times secants to a power, and basically you're going to have another slew of identities that you're going to need to be able to try to beat these problems into a nice familiar form for you. So what we're talking about in this case are problems of the type integral tangent to the power of m, just some power of x, times secant to some power, some other power of x dx. Now the best advice I can give you here is I'm not going to give you too much cookie cutter factor this, factor that, because they're all really different. But the basic idea is you want to end up using the identity 1 plus tangent squared is equal to secant squared. You can look that up in a book. That's a pretty it's kind of analogous to that sine squared plus cosine squared is 1. I mean, this is a fundamental identity. 1 plus tangent squared is secant squared. So what you're going to end up doing is doing some factoring in here and rewriting either one of these in terms of the other, and then doing a quick substitution. And I'm going to show you some problems to show you how to do that. Now here is an integral that's going to be useful as you get to the bottom of the problems here. The following integral is going to be useful. Integral of secant squared dx is going to be equal to 1/2 secant x tangent x, okay, I'm going to continue on the next line, plus 1/2 times the natural log absolute value secant x plus, go ahead and write this as plus tangent x. Okay, so this is a useful integral here. I just put it here because most of the books have this as one of those useful integrals that you can use, and if you can remember it on your test, you know, that's really useful for you to be able to do. So integral of secant squared, 1/2 secant tangent plus 1/2 natural log secant plus tangent, okay? So without any further ado, let's go ahead and work some problems. I think you'll get the hang of these kinds of things once we do that. So what if you had integral of tangent to the 5th power of x times secant to the 2nd power of x dx, and you had to evaluate that integral, okay? Well, we already talked about the fact that you're going to have to use your identity 1 plus tangent squared is secant squared most of the time. But before you do that, you really just want to see if you can do something, you know, even simpler. Now, what if I chose a simple substitution here? That's the first thing you should always do with an integral, is look and see if you can do a simple substitution that can save your bacon and really make it easy. What if I had substituted for tangent? I said u is equal to tangent of x. What would the derivative of tangent be? Derivative of tangent is secant squared. So I would get a cancellation with secant squared. So right away, even if you're not sure if it's going to work out, you owe it to yourself to at least try. Okay? So if I say u is equal to tangent of x, then du dx is equal to derivative of tangent is secant squared of x. And then dx, solving for dx, is going to be 1 over secant squared x du. Okay, just solving for that guy there. Now let's plug him in and see what happens. Integral of tangent to the 5th power, which is going to be u to the 5th power, because that's our substitution, times secant squared of x times dx, but that's defined as 1 over secant squared of x du. Okay? Obviously, you see why we did it. We did it because we wanted to cancel. So what you have is the integral of u to the 5th power du. Now that's a simple integral. I mean, we did a good job of simplifying that. You can integrate this as 1/6 u to the 6th power plus a constant. 1 over exponent plus 1 times u to the exponent plus 1. And this is going to equal 1/6, plugging back in for u, which is just tangent to the 6th power x plus a constant. So the answer is 1/6 tangent to the 6th power of x plus a constant. So this one we didn't really have to do too many games as far as doing a bunch of stuff, but you know, that's what I'm trying to do in this class. I'm trying to give you some practice with some easier problems and then move on into the harder ones. And so the next one will be a little bit more like that last class. It was a little bit more challenging, okay? So let's say you had integral of tangent to the 3rd power of x times secant to the 4th power of x dx, and you had to integrate that. Okay? So first thing you want to do is just see if you can do any simple substitutions. I don't think you're going to be able to find one, because if you substitute for tangent, integral of derivative of tangent is secant squared, that's not going to cancel with anything. And there really isn't a quick substitution that you can do, but here's what you need to start to do. You need to start thinking about the identities that you know. One of the big identities you know is the one given right here. 1 plus tangent squared is secant squared. So you need to be able to you know, play around with that. So let's do that. Let's rewrite it as integral of tangent to the 3rd power of x. And let's rewrite this as secant squared of x times secant squared of x dx. I mean, this may be a dead-end path, but you've got to exhaust a few possibilities to see if it works. Now let's substitute in what we know, that secant squared is 1 plus tangent squared. So let's do that here. Tangent to the 3rd power of x. Now let's substitute here. Secant squared is 1 plus tangent squared of x. Okay? And then this is just going to be your secant squared of x dx. So all we've done is a trig identity substitution there. Now look at here. What would happen here? If I substitute tangent in here, let's say u is equal to tangent of x, and then I make that substitution, I take the derivative of tangent, that's going to give me secant squared, it's going to end up canceling with this secant squared. So anytime I see a potential cancellation, I'm happy. Let's go ahead and give it a shot. U is equal to tangent of x, du dx is equal to derivative of tangent is secant squared x. Then finally dx is equal to 1 over secant squared x du, because we're going to end up needing that to plug into here. So let's go ahead and plug it in right now. Let's rewrite our integral as integral of tangent cubed, but we defined u to be tangent, so it's u cubed times 1 plus u squared, plugging in u for tangent, times secant squared of x times dx, but dx is 1 over secant squared x du. Now you can see right away why we did this. We canceled this with this. Okay, and we were left with the integral of this stuff here, and I'm going to multiply it in. U cubed plus u to the 5th power du. Just multiplying u times u cubed times 1 and u cubed times u squared gives me that right there. And then I can actually integrate this thing right here because it's just a simple polynomial. So that's going to be 1/4 u to the 4th power plus 1/6 u to the 6th power plus a constant. Your simple integration of your polynomial. 1 over exponent plus 1 times u to the exponent plus 1. Same thing for this one, exponent plus 1. Okay, and then the final thing, you just want to plug in what you know for u. Tangent to the 4th power of x plus 1/6 tangent to the 6th power of x plus a constant. 1/4 tangent to the 4th power of x plus 1/6 tangent to the 6th power of x plus a constant. Okay, so you see that these problems are really just an exercise in your identities. And also an exercise in patience, because the first thing you need to do is try about 3 or 4 different ways that don't work. So if I could give you a piece of advice, that is, you see, I'm at a little bit of an advantage here because I've worked these problems, I chose them, I picked them, I derived them, and I made them to hopefully make a class that's good for you. When you're presented with a problem on your test and you have no idea if what the substitution is, you're going to have to make some trial and error. There's no other way around it. So don't get discouraged if you don't see it right away. I mean, you have to play with it. So integral, next problem, of tangent x times secant to the 5th power of x dx. We want to go ahead and do that, okay? Okay, so the first thing I'm going to do is rewrite this, and I'm going to show you something kind of clever. Tangent of x, now I'm going to rewrite the secant as secant of x times secant to the 4th power of x dx. So you see a common theme. A lot of times what you'll end up doing is taking one of the powers and rewriting it as something else to let you make a cancellation. Now let me ask you this. If I were to choose a substitution, u is equal to secant of x, the derivative of secant is tangent times secant from your derivative tables, which would cancel with that. So let's do it. So if we say u is equal to secant of x, then du dx is equal to tangent x secant x, and then solving for dx, because that's what I'm going to need over here, is 1 over tangent x secant x du. And that's going to give us a nice cancellation with this term over here, so we're going to use it, and we're going to say integral of tangent x times secant x times u is equal to secant, so it's going to be u to the 4th power times dx, which is this, 1 over tangent x secant x du. Okay? And you can see right away we did it because this cancels with this. So you'll be left with integral of u to the 4th power du, which is just simply 1/5 u to the 5th power using your exponent rule, 1 over exponent plus 1, u to the exponent plus 1, plus a constant. And then we just substitute what we know u is. 1/5 u is equal to secant, so it's secant to the 5th power x plus a constant. So the answer is 1/5 secant to the 5th power plus a constant. So in this section we have covered quite a bit of ground. We talked about the so-called trigonometric integrals, which are just integrals with trig functions multiplied together, and they usually have powers associated with them. If I could give you one piece of advice, is that this section doesn't have a cookie cutter way of proceeding. You have to use your trig identities, you have to use those helpful integrals I've given you in some of the sections and also listed in your book, and you have to be willing to play with it until you find something that works. But if I had to give you one piece of advice, one more piece of advice to actually do that, when you have powers, Most of the time you need to break the powers up, like if it's sine to the third power, break it up into sine squared times sine and try to use an identity to write one of those things in a different form and then choose a substitution. If I had to pick one technique, that's what I would do. Break powers up, use an identity to make it simpler, and then use a substitution. And there's lots of variations. There's no cookie cutter way to do it, but if you follow that and trial and error and work a lot of problems before you test and review what I've shown you here, I think you can get good at these to do your problems.